Alrighty. Let's talk just for a second about a little more specifics for acids and bases. Okay? Acids produce H plus ions in aqueous solutions. We talked about that. It's usually just by dissociation. If we add an H in the compound and then when it's dissolved in water, we get H plus and then some minus ion. Okay? Bases produce hydroxide ions in solution. OH minus is a polyatomic ion. It's hydroxide. Okay. It works by dissociation in a very similar way for hydroxides, but there are other bases that have a couple more steps to them that we won't worry about it now. So we mentioned that strong acids dissociate completely. They're considered strong electrolytes because they will completely conduct electricity after they've dissociated. There are 6 common strong acids. You should memorize these 6 because there are a billion different acids, maybe not a billion, but there are at least dozens of different common acids, but only 6 of them are considered strong acids. So the easiest way to tell if an acid is a strong acid or not is to just see if it's one of the 6 common strong acids. Other acids will be weak. Okay? So let's remind ourselves how these names work. When it's H plus and just another atom, those are the hydro acids. Hydrochloric acid. Okay. That's because Cl minus is chloride. And that "ide" ending is what causes the hydro to be at the start of the acid name. The hydro doesn't just mean hydrogen because all acids start with hydrogen. Okay? It has to be an "ide" anion in order for it to be a hydro something acid. Okay? So if HCl is hydrochloric, what is HBr? Hydrobromic acid. Okay. What is HI then? Hydroiodic. All right. Now, we got a different ending when we have a polyatomic ion, right? NO3 is nitrate. Okay. So these are the regular ic acids with no hydro. Okay. So HNO3 would be called what? The 8s make an ic ending. So this is nitric acid. H2SO4. That's sulfuric. HClO4. The chlorine ones, chlorite and chlorate, were 2 and 3. Hypochlorite was just 1 O. And what was the 4 O's called? Yep, per. So this is perchloric acid. Okay? And just put the little ditto marks there. Okay? So, chlorine, bromine, iodine, they're all next to each other on the periodic table. And then nitric, sulfuric, perchloric. Those 6 are considered strong acids, which means what do they do when they're dissolved in water? Yep, they conduct electricity because their ions completely, they completely dissociate. They completely separate. Okay, so these are the 6 strong acids, okay, that completely ionize. That's one way of saying it. Completely dissociate. Completely separate. In water. Okay? Other acids. All other acids will be considered weak acids. So notice we had chlorine, bromine, and iodine that made strong acids, but F, which is above those three on the periodic table. HF, even when it's AQ, is a weak acid. Here's H and acetate. So what's the name of this acid? Yeah, this is acetic. Another one that tends to throw people off guard, H3PO4 is phosphoric acid. That is a weak acid. Okay. Now, the important thing to remember here is that weak acids do not separate into ions. In complete or net ionic equations. Okay? Whereas any of the ones in this above list, right, for instance, would become H plus AQ and ClO4 minus AQ. Okay? Any of these would just stay, for instance, HF. Okay? So, don't forget about that. That's a very common mistake. It's an easy thing to overlook. Okay? But if you're doing a chemical equation that involves an acid, okay, and if you have to do a complete or net ionic equation, like you will have to in your lab report, you have to first check to see if that is a strong acid or a weak acid. Okay? That behavior is different. The strong acid is more like an ionic compound. The weak acid is more like a molecular compound. Okay? So don't forget to check that. Strong bases are the soluble or slightly soluble hydroxides. Okay? Any of these would behave just like any other soluble ionic compound. Right? It would become Na plus and OH minus. Okay? And when we mix an acid and a base, we have an acid-base neutralization reaction that works just the same as those exchange reactions that we had before, okay, with those ionic compounds. So we combine an acid and base, we'll produce water as one product. The other product is an ionic compound that's referred to as a salt. Okay. The historic name for salt is the ionic product of an acid-base reaction. It's really just any ionic compound. Okay. But it's called a salt in this context of acid-base neutralization. So why don't you try writing the molecular equation first for the neutralization of nitric acid and calcium hydroxide. Okay. That means writing everything with phase labels. The phase labels for any of these acids will be AQ. I didn't write them in, but we'll pretty much always see these with AQ as their phase label. So start molecular, which means you're writing the formulas with no charges, the formulas all together. Whether or not it is a strong electrolyte, a molecular equation will start with everything all together. Yep. And then you can guess what I'm going to have you do next. You can assume AQ phase labels for acids and bases. They have to be dissolved for the reaction to actually happen. So okay, so I assume you did HNO3AQ. Leave room for a coefficient. What is calcium hydroxide? Like that? Oh, yeah, don't forget parentheses. Hydroxide is a polyatomic ion, so the parentheses around it. Okay. There you go. What is one product? Yeah, H2O. What phase label should the water get? Yeah, H2O gets the liquid phase label. In these kind of reactions, water is pretty much the only pure liquid that is involved in any of these reactions. All of these other ionic compounds and stuff, they're pretty much solids when they're pure, but they've been dissolved in aqueous solutions. But water itself is a liquid. Okay? So do that water liquid. And what's the other product? Calcium nitrate. Looks like NO3 parentheses 2. That's AQ from the solubility rules. Right? We're not going to write the whole net ionic equation here, but let's at least write whether or not the ions would be separated. Okay? For HNO3, should I break that apart? Yes. Okay? So let's just do one of them here. H plus AQ and NO3. I didn't balance this, by the way. What do we have? Did somebody balance this? That's going to be important.
2HNO3 and 2H2O.
Yep. You can get the two nitrates from over here, right? And then it's sort of just a matter of counting the H's that make up the water. So 2 hydroxides, and then you need 2 H's to make waters. So it goes 2 H plus and 2 NO3 minus. Okay? So I'm not going to write all those things. Calcium hydroxide, would that be broken up? Yep, I think so. Water, what about that? No, that is a pure liquid. So we're going to write 2H2O liquid. Okay? And then calcium nitrate gets broken up. Okay? So that was not net, that was complete. Can you sort of tell just by looking at this? I haven't written out all the ions, but if you know how this is going to work, you should be able to figure out what the spectator ions are here. Anybody figure out what the spectator ions would be? Yep, calcium would be a spectator ion, NO3 would be a spectator ion. Okay, so sometime on your own, well, you're going to do it for the experiment. What would be the only things left over then to make the net ionic equation? Yep, it's going to be H plus, OH minus, you would normally reduce the coefficients like we did there. Okay? If it's 2's all across the board, we could reduce it like that. That would be the same net ionic equation for reaction of any strong acid with strong base. Okay? If either of the acid or base were weak, we would have more to the net ionic equation, because a weak acid or weak base does not get broken up into ions. Okay? So you can practice that. I'm going to skip these next 2 pages just for today. We can work on these titration problems at the start of class next time. What I want to do, I want to skip ahead to gas evolution so that the Wednesday people with their lab due on Wednesday know what to do for these. This is just an interesting little thing that happens with sulfides, sulfites, and carbonates. So, what is a sulfide? What does the sulfide ion look like? It looks an awful lot like chloride or bromide or oxide or something like that. So S2 minus is sulfide. Okay. What is sulfite? Sulfate is SO4. Sulfite is SO3. Carbonate is CO3, 2 minus, okay? So, if we have a sulfide, sulfite, or carbonate, they form a gaseous product when we react to them with an acid, and it works like this. This is just an exchange reaction. If you think of ions here, plus and 2 minus, what would one product be of an exchange reaction just between these? Sodium chloride, probably AQ. Okay. Then what? Well, let's just do an exchange. Right. Na plus Cl minus. HS is close. Yep, let's write them based off their charges, right? H plus S2 minus. Okay. Then we can worry about balancing, right? Because we'll probably need a 2 there and a 2 there. H2S is a gas. Well, it's called hydrogen sulfide, as you'd expect. Anybody know what hydrogen sulfide gas smells like?
Rotten eggs.
Yeah, it smells like rotten eggs. Okay. But there's a reaction that directly produces a gaseous product just through its exchange reaction. Okay? So that's why sulfides are on the list, because we got sodium sulfide reacting with an acid. Okay? We make hydrogen sulfide gas. Okay? That's fine. So here we have a sulfite, and this is the exchange reaction. Again, just plus, minus, plus, 2 minus. Okay? H2SO3 and NaCl. I think all of you got to this point in this type of reaction in lab. Okay? You reacted a sulfite with a different acid, I think, but you all got to this point. In order to produce a gas, though, what actually happens is that this H2SO3 product further breaks down into H2O and SO2. There's our gaseous product. Okay. So what you could do is rate these products and then a further arrow, okay, that shows those ones. You'd probably also have to include the NaCl, because that didn't go anywhere. Or it would be equally correct to just start with these two and go straight to these 3. Okay. And so why don't you see if you can write the products of the exchange reaction first. And then do something very similar to what we did up above, where one of the products can break apart into two, forming a similar type of gas.
If it's not soluble, does that mean it's going to be the gas product?
That's not a generalization that I'm comfortable with, but in the case of these, you're making a small molecule, which will be the gas. It's a non-ionic product. So start by doing, plus minus plus 2 minus. Exchange the ions first. And then very similar to up above, show how one of those products can break apart. Guys get something like this for your exchange reaction products. H2CO3 and NaCl. And then what do you suppose happens? Yep, that breaks apart into yep, let's do H2O. Just really pretty much just like up here. And CO2, carbon dioxide gas.
Why is H2CO3 a bird like this?
Well, it's an acid, right? It starts with an H. It's called carbonic acid, I suppose. But, I mean, we could name it like that. It's carbonic acid. Okay. But carbonic acid will break apart into water and carbon dioxide.
So carbonic acid.
Carbonic acid, you could consider that unstable. There's technically there's an equilibrium between carbonic acid and broken apart. But the problem is, once you break it apart, carbon dioxide is a gas and it bubbles out a solution. So it can't really go backwards. So it's really those products that are made. So you should become very familiar then, I suppose, with what happens with a sulfide, sulfite, or carbonate, okay, and exactly how they produce, how they're one of these gas-forming reactions. There's our gas. It's formed right there, okay? So questions about those?